Hello, my name is Alexander Hochwallner, and in this video I'm going to talk about molecular dynamic simulation of the mechanical properties of photopolymers used in 3D printing. I work at the TU Wien at the Institute of Material Science and Technology as a doctoral student in the group of Professor Jürgen Stampfel. Resin development for 3D printing is usually a purely experimental approach where resins are mixed, tested and analyzed. But analyzing is sometimes difficult because some of the properties are not directly accessible experimentally. And a simulation approach could help to make some of the properties more accessible via computer simulation. So we add to the development loop a simulation step to increase the learning outcome of the experiments. So, quick introduction to molecular dynamics, what it is. So basically it's actually very simple. First of all, we need to define particles, the interactions between these particles, and in the final step what the molecular dynamics code does is simply solve according to the particles and the interaction that were defined beforehand, and solving the Newton's equation of motion. The chemical information is brought in via the parameterizing of the molecular system. This can be done in two ways. First of all, an all-atom representation, where every individual atom is represented by one particle in the simulation, and secondly, a coarse-grain representation where a group of atoms is grouped into one coarse-grain bead, which you can see here to the right. And the difference is simply that the coarse-grain representation is computationally much less demanding, but the accuracy is a bit lower compared to the all-atom representation. All-atom parameters were taken from the driving force field, and the Martini parameters for the coarse-grain representation were taken from the reference I put down here. The next step in modeling a photopolymer system is to define the initial box, which is done by a random packing of the molecules. Here you can see 400 reactive molecules plus 5 initiating molecules packed into a predefined box. To get realistic densities, it is then necessary to compress the simulation box with an external pressure of 1 bar to obtain realistic densities, and this is done by the LAMMPS molecular dynamics algorithm, which simply shrinks the simulation box until 1 bar is reached. Okay, the last step then in modeling a photopolymer system is the chain growth polymerization, in the case of a chain growth polymerization, of course. And here a modified version of polymatic was used to perform chemical bonding when a certain criteria is met. And this criteria is simply a cutoff criteria where when two particles that were labeled as active and as reactive are the distance between them is below the cutoff distance, then a chemical bond is formed. So the interaction goes from a 12-6 Lennard-Jones to a bonded interaction, which is represented by a harmonic bond. Okay, here is a video of the simulation itself. This is the simulation of the polymerization of TechDMA, and I only toggled visible the molecules that are engaged in the bonding, so that it is a little bit more, it is better visible, the whole process. So we can see where the active regions are. And in the beginning, the polymerization was pretty quick. And now it is a bit slowing down, but still, now I show a fast forward to the final product. You can see, although we had regions where there is no activity in the beginning, we can see that the polymerization was going throughout the whole volume to form a highly cross-linked polymer material. Okay, now coming to the results of this work. So we'll go through all the stages of the simulation as I explained them before, and we'll explain a bit about the most interesting results, starting from the initial configuration. So after packing of the simulation box and energy minimization and molecular dynamics run. In the case of TechDMA, there's an interesting fact that after the molecular dynamics run, we can see some self-assembly of the molecules, which means that the reactive groups, here the blue beads are the reactive groups, are adjacent in the after a certain time. So starting from a more or less random configuration, the molecules are self-assembled and reactive groups are adjacent to each other. And this is so the reaction kinetics is of course depending on the initial configuration. To the top, at the top right graph, you can see the reaction kinetics of TechDMA. The x-axis are the attempts, which means in the code attempts to form a bond, and if no pair of particles is found to meet the bonding criteria, there is simply a molecular dynamics run, and then the code is attempting again to form a bond. And you can see here in the beginning of the TechDMA that at every attempt one chemical bond is formed. Only here above 30% it is starting to tumble a bit, but still reaction is quite fast, and then it stops abruptly. And when we look at the initial configuration, we can see that some of these reactive domains are very separated. So if one of these domains is reacted, the reaction cannot proceed to another domain, so that the reaction is very quick within one of these domains, and if the conversion of these domains is more or less 100%, it cannot engage with the other domains, basically. This is a bit different in the methyl methacrylate, which is a monofunctional, very small molecule, and we see much more mobility in the molecules. So the green curve represents the reaction kinetics of the methyl methacrylate. So it's also very quick in the beginning, and then more or less diffusion driven, because we don't see these domains like in the TechDMA. We have diffusion of the molecules, and the molecules can engage in the chemical bonding as well. So to the left you can see the simulation of polyethylene glycol dimetacrylate with a molecular weight of 700. And you can see that there are far less of these blue beads, which are the reactive beads, and they are far more the distance between these particles is larger, and it is represented by a very slow reaction kinetics. Different to this is the reaction of a mixture of this polyethylene glycol with TEC-DMA and the monofunctional methyl methacrylate, where we can see a very fast reaction in the beginning, and similar to the neat TEC-DMA, we have a small tumbling, and a bit below 70% double bond conversion, the reaction then stops. So the next step is then, from the final product we can also learn something about the mechanical properties. In this graph you can see a DMA experiment. So the final product was periodically displaced and the storage modulus was measured. The solid blue line is an actual measurement of photopolymerized TEC-DMA, and the data points are 95% double bond conversion, 82, and you can see the material with 82% double bond conversion is pretty close to the experimental values in the range around from 270 to 300 Kelvin. What we also can do is a large strain experiment. So what is done here, we take the simulation box and simply deform it in one direction and measure the pressure that forms, and the results are here in this graph. You can see on the x-axis the strain and the stress at the y-axis, and we can see a nice increase of stress in the low strain region, and then at something about 8% strain we see a peak in the stress, so which is the yield point then, and then a strain softening followed by a strain hardening. This measurement was repeated for lower double bond conversions, and we can see with lower double bond conversion, which is the orange line here, the yield point is simply shifted to lower stresses. And for even lower double bond conversion, we don't really see a yield point anymore. It's probably more like a very viscous liquid, or more like a gel. This brings me to my summary. So a simulated polymerization approach was successfully implemented, which is extendable to other force fields and molecules. The self-assembly of TEC-DMA was revealed via coarse-grain simulation, and this led to a fast polymerization in the early stage and a sudden termination of the polymerization reaction. Low strain and high strain behavior of the simulated material was obtained. This allows an estimation of the storage modulus, estimation of tensile modulus and yield point, and also strain hardening and strain softening behavior can be analyzed. Okay, thanks for watching this video, and also thanks to the Vienna Scientific Cluster, where some of the computational results were obtained. So thanks again, and I'm happy to answer any questions in the discussion. Thank you very much.